So this week, today I'm going to talk about week 4 videos. So I hope you guys had the time to look at week 4 stuff. So this is week 4. There's only one video you have to watch, which is this one, right? And the tutorials, there will be 8 tutorials this week, and 5 of them will be taken by myself, then the other 3 will be taken by Dr. Sexton. All right, just follow the times. You should go to the course syllabus, which is over here, right? You will see the times of the tutorial. Let me show you. So these are the times for the tutorial. As you can see, these are the 8 tutorials, right? Okay, so just whichever you can make it, just go to that one. Okay, guys, right. Okay, let me begin. Right, so the first thing I'm going to talk about is just go through the notes for week 4. Right, so the first so let me switch the camera. So this is here we are. Okay, hope you can see this. This is the best camera I can buy. I know it's not perfect. It's not very good, but I hope you can see what is in the camera. Okay. All right, guys. And if you have any trouble, just let me know using the chat room. Okay. All right. Now, this week I'm going to talk about point estimation. Right. Point estimation is very important in statistics. So let's consider the example here. In this example, you have a population which consists of all men in the UK. And obviously, the population cannot be accessed because there are millions of men in the UK, right? And so we draw a sample, which is a small subset of the population. So suppose we choose 3 randomly selected men in the UK. And the parameter that we're interested in is in the average height of all men in the UK. And once again, you cannot compute the true value. We cannot compute the true value of this parameter, all right, because it's impossible to access the population, as I said, right? So what you need to do is you need to get an estimate which is based on the sample, which consists of 3 men selected randomly from the population. Now the question is, how can we get an estimate based on the sample? All right, now to address that question, let's suppose X1 denotes the height of the first man that we chose, and suppose X2 denotes the height of the second man, and suppose X3 denotes the height of the third man that we chose, right? All right, so the question is how to find theta hat. Now, one way of doing that is to compute the average of the 3 heights and divide, that is x1 plus x2 plus x3 divided by 3. Another way, but this is not the only way. You can also take the average of the first 2, x1 plus x2 divided by 2. You can also take the average of x1 and x3. You can also take the average of the x2 and x3, and so on. So there is no one way. There is no one way to estimate theta, right? And that you can do it in multiple different ways. Now the question is, which one of the estimator is good and which one is not good? And how do we know which of these estimator is the best? Now to answer that question, I introduced 2 criteria. The first criteria is known as the bias and is defined as the expectation of theta hat minus the true parameter, right? And the second estimator is known as the MSE, or the mean squared error, and is defined as this. Now, the smaller the values of these 2, the better the estimator. So the smaller the bias, the better the estimator. The smaller the MSE, the better the estimator. So suppose you have, suppose you have 2 estimators, say theta 1 hat and theta 2 hat, right? Then you will choose the estimator with respect to bias, you will choose the estimator which has the smaller absolute bias. So if the absolute value of the bias of theta 1 hat is less than this one, then you will prefer theta 1 hat to theta 2 hat. And similarly, if the MSC of theta 1 hat is smaller than the MSC of theta 2 hat, then you will choose the theta 1 hat over theta 2 hat. Okay. All right, guys. Any questions? Just feel free to write to me using the chat box, guys. Right. Okay. Next, 3 definitions. An estimator is unbiased if the bias is equal to 0. So unbiased is a good thing. I mean, if an estimator is unbiased, that means it's a good estimator. An estimator is asymptotically unbiased if the limit of the bias is 0 as n approaches infinity. An estimator is consistent if the limit of the MSC is 0 as n goes to infinity. So all 3 properties are good properties for an estimator to have, right? Right. Next, some properties. The first property is that the MSC can be written as the sum of these two, the variance of theta hat plus the square of this. The second property is that if theta hat is consistent, theta hat is consistent if and only if the limit of variance of theta hat as n approaches infinity is 0, and the limit of the bias of theta hat as n approaches infinity is 0. That's the third property. This one, if the expectation of theta hat is k times theta, where k is a constant, then this is unbiased for theta. Right. So these are 3 properties, and I think I've given the proof of them. So this is the proof of property 1. If you're unable to follow this, I'm happy to go over. Are you guys okay with this proof or no? Hello guys, talk to me. Consistent means that consistency means that as the sample sizes increases to infinity, the variability of the estimator approaches 0. That's what this means. So this is a good property because as the sample size gets larger and larger, remember the MSC denotes the variability of the estimator. So as the sample size gets larger and larger, the MSC approaches 0, which is a good thing, right? Okay. Right. All right, guys. So are you okay with the proof of property 1? What about property 2? Are you okay with this proof? I mean, let me know. Are you okay with the proof of property 2? And what about property 3? Property 3 is obvious. I mean, it's trivial. This is the proof of property 3, guys. Okay. All right, guys. All right. So that's the notes for this week. So what I'm going to do now is I'm going to do examples. So I'm going to start as many examples as possible. I know some of you are not happy that I'm not doing enough examples, but you will see next week, that is week 5, I will do about 10 examples. I don't know, some of you, if you look at the video for next week, it contains 10 examples on point estimation. Okay. All right. So I will do plenty of examples. All right. This example. Suppose x1 to xn are IID. IID, by the way, means independent and identically distributed. Right. With CDF capital F and PDF little f. Find the CDF and PDF of this. This is not an example on point estimation, but it is needed for next week. So that's why I want to do it now. All right. All right. So let me we need this example for next week, week 5. Do we need to know the proofs? Yes, you may need to know the proofs. Yes, Mikhail. Yeah. Yes, you may need to know the proofs of the three properties. I mean, they're not really hard proofs, guys. All right, so let Z equals to the maximum. The question is to find the CDF and the PDF of this, right? All right, excuse me, somebody sending me email. Sorry, yes, excuse me. Yeah, okay. So the CDF of Z is, let me use this notation, right, to denote the CDF of Z. It's the probability that capital Z is less than equal to little z, right? And this is the probability that the max of x1 to xn is less than equal to little z, right? Now, excuse me. If the maximum is less than equal to z, then each element within the brackets has to be less than equal to z, right? So this means, right, this is the probability that x1 is less than equal to z up to xn less than equal to z, right? All right, in the next step, I'm going to use, because we are told that x1 to xn are IID, which includes independence, this is what you get, all right? That's because of independence, right? So this follows by independence, right? This step here. All right, now we know that each of x1 to xn has the CDF capital F, right? All right, so that means this is F at Z, and this is also F at Z. So what you have is F at Z power n. All right, so this is the CDF of Z. Now the PDF, of Z is simply the derivative of this, right, with respect to Z. So if you differentiate this with respect to Z, you will get all right. Okay. All right. So just to summarize, the CDF and PDF of Z are given by this. So the CDF is given by this, right? Don, yeah, I will explain. Give me a sec, Don. I will explain why. And the that's because, remember, x1 to xn, each of them has CDF equal to f, right? Each of these random variables has CDF f. So the probability that x1 less than equal to z, you see, by definition, is the CDF of x1, which is f at z, right? Which is f at z, okay? And similarly, the probability that xn less than equal to z, by definition, is the CDF of xn, which is f at z. Yes, that's right. Yeah, that's right. Yeah. All right. So what I have shown you guys is this is the answer to example 1. I hope we will need this result next week. So I'm doing it in advance, guys. So hope you don't mind. Okay. All right. Any questions on this example, guys, before I go to the next example? What is the difference between this? All right, what is the difference? Okay, this guy here is the CDF of Z, whereas capital F is the CDF of x1 to xn. Maybe I should have made it clearer. Yeah, this capital F subscript Z denotes the CDF of the variable Z, which is the max of x1 to xn, whereas capital F without a subscript, the capital F without the subscript denotes the CDF of x1 to xn. And similarly, a little f without the subscript denotes the PDF of x1 to xn, right? Whereas capital F with the subscript z denotes the CDF of z. And similarly, little f with the subscript denotes the PDF of z. I hope that makes sense, all right? All right, so that's example 1, guys. Any other question on example 1 before I go to the next one, guys? Please feel free. Okay, you guys okay? All right, thank you, guys. All right, the next example, example 2, is here the same question, but here we want to find the minimum of the CDF and the PDF of the minimum of x1 to xn. So once again, let me use some of the letters. Say W equal to min of x1 to xn, right? Right. So the CDF of W is, so here, just not to confuse you, capital F subscript W denotes the CDF of W, right? So it's the probability that capital W is less than or equal to little w. Now I'm going to do a trick here. I'm going to write this as, you will see why I'm doing this in a minute. Excuse me. I'm going to write this as the probability that capital W is 1 minus this, right? Which you can do. Now, this you can write as the probability that the minimum right? Okay. Now, if the minimum of a sequence of numbers is greater than another number, then that must imply that every number in this sequence must be greater than W. All right. All right. And in the next step, I'm going to use the fact that the variables are independent. Because x1 to xn are independent, you can write this as like this, right? Okay, now in the next step, I'm going to write the probability that x1 greater than w as 1 minus the probability that x1 is less than or equal to w, right? And similarly, this probability, you can write it as 1 minus the probability that xn is less than or equal to w, right? Okay, in the next step, right, we are told at the beginning that x1 to xn have CDF capital F without the subscript, right? So the F without the subscript denote the CDF of x1 to xn. So what you have here, guys, is this one here is the CDF of x1, which is capital F at W, right? Okay, you follow me? So this becomes 1 minus, okay? Are you guys okay with me or not? All right, so this is the CDF of W. The PDF, you just take the derivative of this with respect to W, right? So it's gonna be d by dw of, okay? Now if you take the derivative, this is what you get. You get n, okay? Are you guys with me? So it's just to summarize, the CDF and PDF of W are given by capital F. This is the CDF given by this formula. Okay, and the PDF is given by this formula here. All right, so that's any questions? So this is the summary of the answer. There's no minus n, so there's no, when you take the derivative, the minus and the minus cancel, so it becomes a plus. Yeah, so when you take the derivative, you have to use the chain rule. I'm sure you know that from your calculus courses. So, all right, so once again, the capital FW denotes the CDF of W, and the little fw denotes the PDF of W, whereas the capital F denotes the CDF of the original random variables x1 to xn, and the little f denotes the PDF of these variables x1 to xn. All right, any questions on this, guys, before? You guys okay with this or not? I mean, feel free to use the chat room. You okay? Okay, good, thank you. All right, next example is example 3. This is a little bit more involved. So here, you have the same thing as before, but we want to find the CDF and the PDF of the maximum of the absolute values of x1 to xn. So let me call this, say, u, just for sake of not, you can call it whatever you like. I mean, so let me call this, all right? All right, guys. So now the question first thing I want to do is to find the CDF of u. All right, so it's gonna be, so this is the notation I'm gonna use, which is the probability that capital U is less than or equal to, say, little u. And this is the probability that the maximum right? Okay. Now, if the maximum is less than or equal to u, then every single element within the maximum has to be less than or equal to. So this will become the probability that right? Okay. Now, in the next step, I'm going to use independence. So this will become the probability that like this. All right. Now, this is where I'm going to use. I'm sure you know this fact that if you have something like, say, absolute value of x less than equal to u, then that's the same as saying that without the absolute value, x must be between. Right? I'm sure you know this result, right? Don't you? I mean, do you guys not seen this before or no? This is, I mean, you might have seen this in your courses, in your previous courses, right? That if the absolute value of x is less than equal to u, then this must be true, right? So using this fact, you can write the above as the probability that like this, all right? Okay, now I'm gonna, this guy here, I'm gonna write it as follows. You can write it as the difference between the probabilities okay? I mean, the probability that x1 lies between minus u and plus u is it's the same as the difference between these probabilities, right? And the same thing here. Okay. All right, guys. Now we are told that each of these variables has CDF equal to capital F. So what you have here is capital F at u minus capital F at minus u, right? And the same thing here, capital F at u minus capital F at minus u, right? So the answer is, so this is the CDF of u, right? Okay, now to find the PDF, you just need to differentiate this, right? So I'm going to denote it by little f u like this, right? Now you should differentiate this with, again, you have to use the chain rule. I'm sure you did your chain rule in your calculus courses. I know some of you might have forgotten, but I suggest you look up your calculus courses you've taken. So if you use the chain rule, guys, this is what you will get. Right, this is what you will get, right? Because it becomes a plus because you have minus minus, so minus minus gives you a plus, right? So just to summarize, the CDF and PDF of U are, so the CDF is given by right? This is the CDF of U, and the PDF of U is given by all right. Okay, guys, any questions on this? I mean, let me highlight this once again. So this is the result I wanted to prove that, right? Any question? Are you okay with this, guys? That this, by the way, once again, this notation is the notation for the CDF of U. This is the notation for the PDF of U, whereas capital F denotes the CDF of the variables x1 to xn, and little f denotes the PDF of the variables x1 to xn. All right, are you guys okay with this? Please talk to me, guys. You okay? Good. All right. So that's example 3. Example 4 is the same example as example 3, but here we are interested in the minimum of the absolute values of x1 to xn, right? So let me call this V. Let V denote the minimum okay. So the first thing I want to find is the CDF of V is like this, all right? And this you can write by the complement rule. This you can write as the probability that capital V is greater than little v, right? And this you can write as the probability that like this, all right? Now, if the minimum, if a minimum of a sequence of numbers is strictly greater than something, then every element in that sequence must be strictly greater. So this is the same as saying the probability that the absolute value of x1 is greater than v up to okay, like this, right? And in the next step, I'm going to use independence. We are told that the variables are independent, right? So we can write this as like this, okay? Right now, okay, in the next step, I'm going to use the following fact. I'm not sure, I don't know whether you know this, that if the absolute value of a random variable is greater than, yeah, I will go a little bit slow, okay. Yeah, I'll try to go a little bit slower, but I'm trying to do as many examples as you can because that's one of the comments. Oh, okay, you're right. Yeah, thank you, Vikram. There should be I'm missing out a 1 minus here. Excuse me for this. There should be a, thank you for that, Vikram. Yeah, there should be a 1 minus, 1 minus, 1 minus here. All right. So what I was trying to say is that if the absolute value of x is strictly greater than something, that's the same as saying that either x is greater than v or x is less than minus v. I hope you know this. You know this following fact that, all right, okay, so using this result, you can write the above as I'm sorry if I'm going fast, but I'm trying to cover as many examples as possible. I mean, you know, so I hope you don't. I hope. I mean, you're most welcome to use the chat room to ask any questions you guys have. Right. All right. So using this fact, you can write the above as this and this as this. Now, because these two are mutually exclusive events, you can write this as right. Right, that's using the fact that these two events are mutually exclusive. That means they cannot occur together. So this probability must be the same as this sum of probabilities, and the same thing here. And in the next step, I'm gonna write the probability that x1 greater than v as 1 minus the probability that x1 is less than or equal to v. Okay, and the same thing here. Okay, all right, okay, and in the next step, because what you have here is the CDF of x1. Okay, so this becomes f at v plus f at minus v, right? And the same thing here, 1 minus f at v plus f at minus v. Okay, so this becomes 1 minus, okay, like this, right? So this is the answer for the CDF. Now to find the PDF, you just differentiate this with respect to v. So let me denote this by this. So you differentiate like this, right? Now, if you use the chain rule, to do the differentiation, this is what you will get. Correct me if I'm wrong. All right. Then you have minus. So this will be f at v. Okay. And here you have plus all right, this is what you will get. All right, okay guys, I know maybe some of you are confused, I don't know, but I mean, I know it looks kind of complicated, but it's not really that complicated. I mean, please, are you guys okay with this or no? Or no? You sure? Yeah, I mean, if you have any questions, just please feel free to use the chat room. All right, so just to summarize, this is the CDF of V, and this is the PDF of V. I have used the chain rule to get the PDF, right? All right, so that's example 5. Sorry, example 4. Example 5, this is an example on the stuff we did cover today. Oh, I got one question from Neil. Yes, how minus FV goes to plus? That's because I used the chain rule. So if you use the chain rule, right, to differentiate this, you get minus FV, which becomes minus becomes plus. Do you follow that or not? You have a minus in front here, right? And when you differentiate inside the brackets, you get minus. So it becomes a plus, right? Okay, guys. All right. The next example is example 5. This is something we talked about today. Suppose X, you have a Poisson variable, and the question is to find the bias and the MSC of the estimated lambda hat, which is equal to X. All right. To do this, shouldn't be difficult. Bias, okay, bias of lambda hat, using the definition I gave you today, a few minutes ago. This is the definition I gave you, you may recall, right? So this is the same as the expectation of X minus lambda. Now, I'm sure you guys know for a Poisson variable, the expectation of a Poisson is lambda. So this is 0. So this implies that lambda hat is unbiased for lambda. Remember, an estimator is unbiased if its bias is 0. Now to find the MSC, of lambda hat, right? Remember, by property 1, one of the properties I proved today was that MSC can be written as the variance plus the square of the bias. Right, this is property 1, which I talked about earlier today. No, it's not always the case, Vikram. In this question, lambda hat is X, yeah, but it may be different for different questions. All right, the variance of lambda hat is the variance of X. Right, now bias we know is 0 from earlier, so 0 squared is 0. Now the variance of a Poisson is lambda. Right, so this completes, this is a very simple question. So in this question, I worked out the bias of the estimator to be 0 and the MSC of the estimator to be lambda. You guys okay with this or not? Can you explain the bias again? All right, the bias, all right. The bias is defined, I mean, if you look at the definition I gave you a few minutes ago, the bias is defined as the expectation of the estimator minus the parameter. So the expectation of lambda hat minus the parameter, which is lambda. Now, lambda hat is taken to be X in this example, right? So that's expectation of X minus lambda. The expectation of X is Poisson variable with parameter lambda. So the expected value is lambda minus lambda, which is 0. All right, Vincent, is that clear, Vincent? Okay, thank you. So any other questions on this example, guys? Talk to me, guys. Are you okay with this example or not? Okay, thank you, guys. All right, the final example I'm going to do is example 6. So here, suppose you have a random sample from an exponential distribution with parameter A, and we want to find the bias and the MSE of A hat, which is taken to be the sample mean, right? All right, the first thing I want to do is to find the bias. Let me put this over here, so sorry. So to find the bias of A hat, which is the expectation of A hat minus A, right? And this is the expectation of X bar minus A, and this is the expectation of minus A, right? Okay. Now, if you take the expectation inside, guys, you get 1 over n times the sum of the expectation of xi minus A. Now, you may remember from probability 1 that if you have a variable x that has an exponential distribution with parameter A, then the expectation of x is equal to 1 over A. Do you guys remember this or not? This you should have learned this. I mean, if you don't know this, you try to remember this, guys. You should have, this is a fact that for an exponential variable, the expected value is 1 over A. So this becomes 1 over n times the sum of 1 over A minus A, right? And this is 1 over n times n times 1 over A minus A, which is 1 over A, and this is not equal to 0, right? So what this implies is that A hat is a biased, it's a biased estimator, because remember, a biased estimator is not a good estimator. That means an estimator is good if it is unbiased or asymptotically unbiased. But in this case, it's neither, because you're getting a bias which is 1 over A minus A, which is clearly cannot be equal to 0, right? Okay. All right. So that's the bias. Now to find the MSE of A, once again, I'm going to use property 1, which is which says that this is the same as the variance of A hat plus the bias of A hat squared. All right. So this you can write as the variance of X bar. The bias we already know is 1 over A minus A squared, right? Okay, so this becomes the variance of like this, right? Now, if you take the variance inside, guys, you will get 1 over n squared, because when you pull n, the constant outside, it becomes n squared times the sum of the variance of xi. Now, you may know from probability 1 that, no, if you don't remember, I will write it down here. If x is an exponential variable with parameter A, then the variance of that parameter, of that variable, is 1 over A squared. Do you guys remember this or not? Yeah, I mean, it depends on what A is, but in general, we don't know the value of A. So I mean, in this case, I mean, A is unknown. So in general, this is not equal to 0, right? Okay. All right, the variance of an exponential is 1 over a squared, guys, right? So you should put that here. 1 over a squared plus this, right? And if you simplify this sum, you will get the following. You get 1 over n times a squared, right? Plus all right. Okay, guys, so this completes exercise number 6. So I've done more than, I guess 6 examples is I guess is a good number of examples. I can do more, but I need I know I can do more if I have more time, but I hope you guys learned. I know I have gone fast in some of these examples. It shouldn't be n squared. So it's not n squared because you have an n here cancels with n squared, so it should be n. Remember, when you take the sum of 1 over a squared, it becomes n divided by a squared, right? So the n, that n cancels with this to give you an n. Now, in this question, to answer your question, Vikram, it's just like in this question here that we are taking the estimated to be sample mean. An estimator is a random variable by definition. I mean, an estimator is a random variable, right? And in this particular question, the estimator of a hat is is taken to be the sample mean, right? But in another question, it could be something else, like for example, the sample median, or the sample range, or the sample quartile, or something, right? So it depends on the question. Like, I mean, next week in week 5, we will do 10 more examples of this kind. So I hope you get a thorough understanding of it next week, I hope. But, and to answer your question, an estimator is a random variable by definition, right? Right? Okay. To answer your question, Cheng, yeah, the n squared here cancels with the n here. So what you get here is an n, not n squared. All right, I hope you get it. All right, guys, so this is the end of this session, but we have a tutorial starting at 11 a.m. That is in 6 minutes time. So please do come to the tutorial at 11 a.m. UK time, all right? We will go through the tutorial sheet as usual I will try to go through every single question in the tutorial, right, as usual. All right, guys, have a great day or have a great afternoon or morning. All right, I'll talk to you soon in a few minutes, right? Okay, guys, thank you.